Okay, this is our third example of calculating an equilibrium constant given some conditions. Let's go ahead and read the problem, and we'll show a fast way to do this as well as the reliable but slower ice table method of doing it. In some kind of container that initially has hydrogen sulfide at a pressure of 10 atmospheres. Let's point out right now that they're going to give us lots of pressure data. You can treat this exactly as if it were concentration data to solve the problem. It's 10 atmospheres for initial. That's not our equilibrium data, it's the initial data. It's going to get shifted by a stoichiometric amount. They tell you it's at 800 K. We don't care except to know that it's constant. So therefore, it's valid to do this sort of analysis. The contents are decomposing. Hydrogen sulfide is turning into hydrogen plus sulfur. When the reactions come to equilibrium, they tell you that the sulfur concentration is now 0.02 atmospheres. There's a lot you can deduce from this. Always start by writing the equilibrium constant expression. It's going to be equal to the concentration of these products divided by those reactants. Does anything get omitted? No, they're all in the gas phase. Are there any coefficients? In this case, two, the hydrogen and the hydrogen sulfide. So raise those to the second power. And plug in anything you can. The only thing you can plug in is the equilibrium data they give you, and there's only one piece of data, 0.02 atmospheres. A seemingly unsolvable problem, except that stoichiometrically, if the sulfur goes from 0, which it was in the beginning, to 0.02, the other ones are going to go down by twice that amount, since every two of these forms for one of those, and every two reacts of those for one of those. So let's see. We can say that this concentration is going to go to 0.04 from 0, since two of them are forming. Twice as many of them are forming. And this will go down by 0.04 from 10. Not much of a change, by the way. And so we now have everything. There's your numbers. Turn them into a big number. That's your K sub p. 3.2 times 10 to the minus 7th. That should be an exponent. That's a lousy equilibrium constant if you're trying to get very far. So it's not doing much. The ice table method is slower but more reliable. Start by writing the exact same stuff and then draw your ice table with the balanced chemical reaction, sometimes called a Rice table, up there. Initial, change, and equilibrium. The initial concentrations are given for one of them, right? The change is given since, the final equilibrium value is gone here, so the change can be deduced. This went up by 0.02, therefore these both must go change by 0.04, plus 0.04 for forming product, minus 0.04 for reactant reacting, giving you the same values. Plug in, and there's your final answer. Once again, this should be 10 to the minus 7th power. That's a third example of an equilibrium constant problem.